Awesome. Thank you all for being here. This is atoms versus bits, so we're going to be talking hardware, everything from carbon capture fuels to nuclear fusion to the space industry to hypersonics. So lots of hardware-focused things. So really excited about this. I'm Skyler Shuford, but we'll go through a quick round of intros so you know who you're listening to here, and then we'll crack into all the things where we're seeing trends moving maybe away from software, or at least enabled by software, into more hardware domain, into deep tech, into hard tech, and beyond. So with that, I'll kick it off. We'll start on the other side here with Lauren.
Yes, it's working. Hi, y'all. I'm Lauren Lyons. I am the founder and CEO of a new company that's still in stealth, but focused on the hardware at the intersection of climate and aerospace. And prior to that, I was the chief operating officer of a rocket company in town called Firefly Aerospace. And before that, I was at SpaceX and Blue Origin.
Casey.
Hi, my name's Casey Handmer. I'm a recovering physicist. I did my PhD at Caltech, and then I went to Hyperloop for 2.5 years at JPL, working on space robots for 4 years, and then founded Terraform Industries, which is capturing CO2 from the air and turning it back into carbon neutral methane fuel at cost competitive prices.
All right. Good morning, everyone. I'm Darby Dunn. I'm the VP of Operations at Commonwealth Fusion Systems. We're a clean energy startup that spun out of MIT about 5 years ago, hoping to be the last clean energy source the world ever needs with fusion. Before CFS, I was at SpaceX for a decade, knew Lauren very well, and led the manufacturing engineering team for the Dragon spacecraft, both the cargo and the crew vehicles.
Awesome. And Skyler Shuford, one of the co-founders and chief operating officer of Hermeus, where we're building hypersonic aircraft to radically accelerate air travel, mostly focused in the near term in the national security sector. So really fast planes. New York to London, 90 minutes is our tagline for the vision vehicle when we start working on some of the commercial stuff. But to kick it off, really wanted to start talking, why the things that we're working on may or may not be on the edge of insanity. So why these types of things are, ripe for disruption. And so the first question I'll ask is for Lauren, what sort of things in the space industry, given your background, do you feel are absolutely ripe for change and moving us towards that vision for 2050?
Great question. So right now, with SpaceX's success that a lot of people know about, what SpaceX has been able to do in terms of driving down the cost of launch, you hear this a lot. Like, it used to be getting to space was so hard, so we don't really go very much. But now that, it's relatively cheap, you can get to space for, $1 million. People are doing it now. And so what that does is enable so many more ideas that people were like, well, this is too expensive to even go into this business. I can't even try this. Now, a college student can send a satellite to space. There's so many new space startups that are being founded to address everything from, Earth observation, checking out wildfires, and being able to predict or see a wildfire super early and actually drive action on that. Before that wasn't possible. You can throw up an entire constellation of satellites in low Earth orbit versus a decade ago that really wasn't a thing.
Yes, there's the old adage, which is like, how do you make $1 million in aerospace? And it's to start with $1 billion. I think a lot of folks are realizing now that it's like there is money to be made and there's impact to be had, even though the timelines are long and the costs are super high. Casey, so go a little bit into what you're working on and why is now the right time to start bringing carbon capture into fuel generation into the industry.
Yeah, I mean, approximately it's because climate's a really big problem. And so it's time to kind of get the best people working on this and work on it. But actually to go off what Lauren just said, what we've seen in aerospace is kind of the emergence of business models that can function in the space without needing as much government support as they might have needed previously. Like aerospace has been around for a long time, but primarily it's been government business. And so for us, we're actually trying to, basically pioneer a business model that can use the engine of capitalism, just regular old demand for fossil fuels, to instead, substitute in a non-fossil form of completely substitutable hydrocarbons.
Why do you think now is the time to where we can actually use the commercial sector to do this? What has changed economically or within the markets that allow it to be a non-government driven industry?
Yeah, so there's two key aspects there. Generally speaking, permissionless entrepreneurship has kind of grown outwards from primarily like Silicon Valley software-based stuff into adjacent hardware fields. Not all of them, and not necessarily completely with 100% success, but it's certainly something where ambitious people can look out and see that's possible. And then proximally to us in particular, we were really inspired by cost curves in solar and wind, and no doubt in fusion. But essentially, when solar power in particular is cheap enough, it actually becomes cheaper to turn atmospheric CO2 into fuel than to burn fuel to make power. So you basically reverse the process.
So it's to kind of parrot that back. It's really, it has to be complementary. Like none of this can exist in a vacuum. And so the fact that other technologies are coming along are what enables these types of things to exist in this way. Do you agree with that?
Yeah.
Okay. Cool. Nice. Darby.
Yeah, I think to kind of expand on that as well, fusion is ripe for disruption now. Because there's a new type of superconducting material called high-temperature superconductor. It's been used in a lab for roughly 20 years, only at very, very small scales, and we said, all right, we actually want to learn and produce a whole bunch of this and actually use this for fusion power plants. And that technology allows us to build superconducting magnets that are twice as strong as anything that's ever been built before for fusion. And then I'll spare you the physics equations, but you get 2 to the 4th power, 16 times more energy out because those magnets are twice as strong. So that allows us to finally cross the threshold of net positive energy from fusion and allows us to build it in a much smaller device. So if you Google something called ITER, I-T-E-R, that's a fusion device being built in southern France. It is massive. They started that project in the 90s. They're hoping to get net positive energy sometime in the 2030s. We started as a company in 2018, and we're going to get net positive energy hopefully by 2025. So that's really a lot.
Yeah.
Yeah.
That's impressive.
Didn't shake that up. Yeah.
And really, that is driven by the approach. So it's driven by the ability to produce these things at scale and to bring them together in a way that isn't as large. So I think there might be some similarities within aerospace where new developments, at least within aerospace, are exponential on vehicle mass, the costs of those development programs. Is it the same within your sector?
Yeah, very, very similar. And we're taking something that's generally only been done at a national lab or a nation state level. I think very similar to when I started at SpaceX back in 2008, that we came in as this small commercial player in the game and said, we are going to do something that only countries have done before. So it's similar in that way of, we are taking, hope to be the first commercial company to produce net power from fusion.
That's awesome. Yeah, at Hermeus with what we're working on, so with hypersonic aircraft, it's something that's been 20 years out for the last 50 or 60 years. The kind of key enabler for us is to take existing technologies, so things that have been flying for decades, ramjets rather than scramjets, regular jet engine at low speed, and then nickel-based alloys and metallics rather than getting into exotic ceramics and things that haven't been produced at scale. Sticking in the realm of what are the technologies that are in production and capable right now that we can drive into their extreme, like the full envelope of what these are. So our challenge is less so about any sort of fundamental research, but really about how do you bring these things together. And I see that sort of as a common thread throughout any hardware-based startup is how do you bring the technologies together and align the business case and roadmap alongside. Any other things that you wanted to talk about in terms of maybe the specifics around the technologies to allow some of the folks here who might be wanting to nerd out a little bit in terms of we'll start with you, Darby, on what Commonwealth is doing and what is sort of the specifics around the technology itself.
Sure. So there's 2 broad types of fusion. One is using a laser-based approach. So if you followed the news with the National Ignition Facility, they were the first in the world, or first in the universe, at least human-wise, to get net positive fusion energy. So that's one approach. That generally starts with taking a small bit of fuel, in this case hydrogen, shooting it with a whole bunch of lasers, and then using that energy to convert the hydrogen into helium, and then that is how you get your, E equals mc squared gets you a whole bunch of energy out. The other type of fusion research or production is with magnets. So that's the approach that Commonwealth Fusion is taking. So that is taking these massive magnets and using those to force those hydrogen atoms to fuse together and get you your energy out. So that's the approach that we're taking. The type of device that we're building is called a tokamak. So it's a Russian acronym for magnetic confinement device. There's been about 150 of those built around the world over the last 50 years. But they all have not been able to get over this threshold of net positive energy, mostly due to the magnetic field strength. So that's what we've been working on. Our goal when the company was founded in 2018 was to build a fusion relevant scale magnet that would actually get to that peak magnetic field of 20 Tesla. And to put that in perspective, a typical MRI machine is anywhere from 1.5 to 3 Tesla. So we're roughly 8 times stronger than a very strong MRI machine. So that allows us to actually force those hydrogen atoms to fuse together. So we're currently working on our demonstration device that we call Spark. So it's about 30 miles outside of Boston. And the goal is to turn that on in 2025. And we're aiming for, so the ratio is what we call Q, so power out over power in. You need that to be greater than 1. We're going for Q of 11. So we're saying let's not go to 1.1. Let's go to 11. So that will prove out a.
Is that the only reason you did? It's just like, I'll turn it up to 11. Like that's.
That was definitely an influencing factor. And then once we've proven out that technology, we'll build an actual power plant. So that will be TBD place in the world. We're already having initial conversations on where that will be. And that will be actually producing 400 megawatts of power output directly to customers on the grid. And our goal is to do that by the early 2030s. So
That's awesome. Yeah, that's great. Cool. And so, given that we will have all of this, abundance of energy, and now that in terms of enabling the carbon capture, so it's like, what can you use that for, Casey, to really make 2050, green but still well powered?
Yeah. Well, actually, I just wanted to point out 20 terawatts. 20 Tesla. Sorry, it's been a long day. 20 Tesla. To give you an idea how strong that is, you can levitate a frog in 20 Tesla. You might have seen a photo of that. That's that sort of magnetic field strength. I don't think that the Spark system is designed to levitate frogs primarily. But
I don't think a frog would do very well.
It's completely
their
fine.
System.
It's just like it's got water in it, right? Like us, it's weakly paramagnetic, and it's kind of can float there.
yeah, we did actually do some math and say, could we levitate a truck on top of this? The answer was yes.
Oh yeah.
The safety folks were like, please don't do that.
Just don't do that. Yeah. Well, yeah. So for a hot minute at Hyperloop, I worked on magnetic levitation there. So I became quite good at figuring out how much magnets you need to pick things up. So I'd say, as far as what we're doing, it's nowhere near as exciting, frankly, as Hypersonics or fusion, in that the nuts and bolts of how we're executing is really about delivering extremely low cost stuff, right? So it has to be really generic and really simple and really manufacturable, because we need to make millions and millions of these things in order to do this at the relevant scale. But the reason it's possible is that I have a whole bunch of different factors of production. I've got to pay for labor, I've got to pay for materials, I've got to pay for land, I've got to pay for energy, obviously. Almost a simply staggering quantity of energy. 400 megawatts is a nice number in order to substitute all 50 gigatons of CO2 that's emitted every year by people around the world, in addition to increasing access to cheap hydrocarbons for parts of the world that don't have that yet. We would need it more like 400 terawatts, which is about 1 million times that. So get cracking. But of those factors of production, only energy is currently getting cheaper. Labor and materials are getting more expensive gradually, but energy is getting really cheap. And just to go back to solar for a second, solar since 2010, which is when I immigrated to the United States, has come down by about a factor of 10 in cost, which is staggering. I mean, imagine if Starbucks was 10 times cheaper since 2010. That's but solar is that much cheaper now, and so.
What's driving that? Why is it so much cheaper?
Economies of scale, essentially. So the manufacturing rate has also increased. The manufacturing rate increases about 30 or 40% per year since 2010, actually since 1970. And then for every doubling of production, the cost comes down by about 30%. So all in all, it works out to something like 10 or 12% cheaper per year, which is super enabling for a whole bunch of really exciting stuff, not just synthetic fuels, but like new ways of mining and extracting stuff. Like I'm talking about abundance here, like post-scarcity energy abundance. People have been talking about it for a long time. It could actually happen pretty soon, which is super exciting. And so yeah, basically, this is the one thing. If you remember one thing from this panel, this is the thing that will blow your mind. How do we build a system that captures upside from power getting cheaper? Right. So if we think power is going to get cheaper, the way we capture the upside from that is we deliberately make our system energy inefficient. All right?
Okay, keep going.
Okay. So generally speaking, with the sort of systems we're building an electrolyzer, we're building a carbon capture rig, we're building a what's called Sabatier or methanation reactor that combines CO2 and hydrogen to make natural gas. In all these three systems, there exist extremely high performance versions available, not necessarily in the open market, but you can go and hire an EPC company to make them for you. And in all these cases, and the last 50 years of academic research and so on, has been about spending exponentially more money to gain at most linear increases in efficiency. And this has made a lot of sense. If you're paying $400 a megawatt hour for power, then you're going to be losing money making hydrogen with bioelectrolysis as opposed to steam reformation anyway. So you may as well pay up front a huge sum of money to get 80, 82% efficient electrolysis. But if instead you take that trade and you flip it around, and this actually comes back to a bit of what you said about Hypersonics, in terms of using existing generic materials or existing technology and basically taking it to its limit, you get exponential cost savings for only linear decrease in efficiency. So it just happens that our electrolyzer is spec'd for about 50% efficiency. So it's only 30%, well, it's like 80% minus 30% is 50%. But because we do that, we can cut the cost by a factor of 20 or 30, right? So we end up using about 30% more power and we end up spending 20 times less money building these. So for the same money, we can build 20 times as many.
It's actually really similar to the innovations we've been doing with the superconducting material.
Yeah.
And at a lab scale, from a pure research perspective, the idea was how do you make that superconducting material the best that it can absolutely be? How do you make it super, super efficient, get the most current through the most square inches that you can? And instead, we turned that on its head and said, actually, we don't need the highest performing superconductor. We need a lot of it. So that was actually the trade. Was can we change, flip the equation from focusing on best performance to instead mass or more volume? And yeah, dramatically cut down the costs, and really was that key switch for our suppliers to actually produce the volume that we need.
So in terms of, rather than optimizing for amps per square millimeter, which I don't know, it's probably in the thousands at least, right? You're optimizing for amps per dollar.
Mm-hmm. Yeah, I think that's an interesting thread, and we'll talk more about what you've seen in the space industry and on the rocket side especially. But it's it's getting to scale. What ends up being I think the biggest difference between atoms and bits, right, is there's an inherent scalability of software where it's a lot more difficult because the transition from R&D to production is so much different in hardware. So I think that's a super interesting idea. I think it's originally. One of my other co-founders came from Blue Origin. I think it was originally from Jeff Bezos, but taking an architecture that has high performance, but detuning in any of the individual subsystems, and that's what allows you to get R&D very, very fast. And then you start bringing up and bringing them alongside. But because you're detuning some of these systems, it gives you more margin to play in, given all these broad uncertainties of the envelopes that you're playing in. So, getting towards the differences in approach, the similarities in approach between hardware and software. Lauren, what have you seen in the multiple space or the rocket companies that you've worked for in terms of the approach to R&D that manages this complexity and uncertainty, especially as we're talking about scale and how we get to scale?
Yeah, one of the biggest things, I guess, even though hardware, there are a lot of hardware startups, and people are taking, what used to be a way to lose a lot of money really fast, and now going, hey, we're going to build rockets. The margins are still super tiny. And if you look at a company like SpaceX, if they only launched rockets, well, again, the margins are super tiny, so they've gotten into satellite internet. And that will bring in the money. But I think in terms of that production process, or that R&D to production process, what I've seen is you are constantly in a race against the clock. You're like, I only have this many millions of dollars, and I have all these mouths to feed. and I have to build this thing. And so I think part of what drives some of the simplicity aspect, and by simplicity I mean like first principles thinking, like what does the system need to be? Yes, there's what NASA used to do, there's what the space shuttle used to do, but there was a different budget, a different time, and a different risk appetite. So if I say I have this many months of runway, I can either spend those entire, like a year, let's call it. I have a year of runway. I can spend an entire year getting it perfect. I can build the perfect machine. I can put analysts on it for that whole year, and we won't really build much, but we're going to design something perfectly. How often do things
on paper?
On paper, right? We can paperwork engineer this thing. We're going to have it in CAD. It's going to be great. It's going to be all these simulations. Then you build the thing, and then didn't do.
We forgot something.
Yes.
One of my least favorite phrases to hear from design engineers is, well, it worked in CAD.
Right, exactly.
It's easy. Yeah, it always works in CAD.
Right, and then you get the pieces and they don't fit together. So instead what you say is, you know what, we're not gonna hit perfect. Instead, like, what do we need to de-risk right now? What do we need to learn right now? Let's build that now. Because I would rather like blow a bunch of stuff up by failing and get to that answer faster than design it in CAD perfect and then still have a maybe 50-50 chance of it working.
Yeah, because that risk still exists. It's the unknown unknowns that are going to get you in this business, right? And so you have to drive as aggressively as possible. I think that is where there is a big similarity, which is like the fail forward, fail fast. I don't love fail fast because it implies like you're optimizing for failure, but it's more just like be robust to failure and drive it as aggressively as you possibly can. And I think that's something that is shared with software, and that like agile approach is what is enabling a lot of these technologies to be able to come online, as long as your architecture and your business are both like resilient to the ability to like be dumb about something and learn from it.
Well, and it also what drives, like, just to use SpaceX again as an example, like building a water tower out of stainless steel. Like that is cheap. I can do that tomorrow, right? Like I don't have to have some special material or, do any science in order to do that. And so if you're going to, these like economies and being able to build this complex hardware in a startup environment necessitates taking a more fundamental approach to things.
So yeah, I guess let's go a little bit deeper. In terms of like driving that simplicity, Casey, how are you thinking about it for your business on how to drive simplicity into the designs to make sure that you are able to get to those unknowns faster, and being able to scale it as you think about abundance of energy and being able to like provide these fuels?
Yeah, so the critical thing for us in the design and kind of prototyping phase is, I call it closing the OODA loop really quickly. So the observe, orient, decide, and act. And so the way that translates is that we very small teams working on each of these three subsystems in parallel. They're not blocking each other. They have the resources they need, and they can iterate the design extremely quickly. They can try out crazy ideas, but there's no assumption there that they'll go through analysis paralysis for 6 years, then build the thing and it'll work perfectly the first try. It's mostly about exploring design space and seeing how that works. And then I guess the other thing is, our intent long term is to do essentially localization of production. So rather than having like one factory somewhere that produces all these things, we actually want to have like one factory per city. And so generally speaking, I say for supply chain, you can use anything you can find in Home Depot. Or
McMaster, that's our go-to.
well, actually, so I mean, if you're setting up a factory in like, Nairobi, you don't have a McMaster. Yeah. So like if we can build this out of generic building materials, which for the most part we can, not everything, but mostly, then that's drastically simplifies our supply chain, right? And we're in this for the long haul. We're in here to build hundreds of millions of these machines long term, and we will, not be able to reach meaningful scale on a climate front if we run into some fundamental supply constraint. Like, it turns out we need 8 times more iridium than exists in the Earth's crust. That would be bad.
Certainly. How is Commonwealth and how are you thinking about, complexity management of an inherently, I assume, very complicated system?
Great question. Yeah, I mean, we actually have a document in the company we call the 10 things we know to be true. And one of the 10 things we know to be true is that, making something that is simple, that is robust, that is reliable, like those are absolutely key tenets. So I think that hits a lot in our thinking, in our design reviews, is how do you make something that is this combination of simple and robust. And I think maybe a good example is that, coming from the aerospace world, you had to try and make everything as absolutely lightweight as possible, right? It's like every pound.
Mass is too high, always.
Yes.
Is it low? No, it's always high, every time.
Yeah. So that actually has been a really interesting mental shift for me of, the weight doesn't matter. And so you're like, all right, let's make something simple and robust instead of doing, some crazy design features to, do some, ISO grid pattern to get strength plus, low weight. Instead of like, just do a giant block of steel. So I think that really helps that, we have that benefit to help simplify the design. And then as well, like we spun out of MIT. We actually still have a collaborative partnership with the Plasma Science and Fusion Center at MIT. And so it's also this combination of, using a very research and analysis-based approach to try and figure out how to try to simplify those designs as well. So we can be off to the races on an R&D project and say, all right, how do we, this is the way that it's been done in the past. How do we figure out how to do that differently? And actually, one of the magnet designs we came up with is dramatically simpler than these type of superconducting magnets that have been built before.
So to go a little bit deeper on that, I think there's almost, in terms of approach, an inherent rub between research and building things. It tends to be where you're trying to get into the kind of extreme environments and where you have to get almost like more complicated or like change your approach in a very interesting way. So how have you been able to balance the like research focus, which I think has, not inherently, but like has a tendency to lead towards analysis paralysis, to use Casey's term, but balance that with like getting in the right neighborhood and then going to build the right thing. So what has worked in terms of like marrying those two sort of approaches?
I think it's been generally a very symbiotic relationship at CFS, which has been great. And we're able to allow the physicists time to think, time to ideate, time to run their models, figure out better and better solutions, and then we are partnering that on the manufacturing side of, okay, once we have those ideas from the physicists, they're like, all right, here, go do this. We have set up manufacturing processes that are able to iterate on that really quickly. So we're trying to buy them as much time to do that analysis, to do that ideation, to be really, really creative on these designs that have never been done before. And then we have shortened our manufacturing time, through a lot of, in-house tooling, really rapid prototyping, and trying to make that turnaround time really quick. And then also getting enough of those projects in the works, so that way we can, keep, we're not waiting to do everything in series. We're able to parallelize a lot of that.
So like really focusing the expertise in only the places that it needs to be focused, and really bringing everything else alongside to where you kind of parallelize it. That's does that kind of match, as a recovering physicist, as you said, does that kind of match how you see Terraform growing in terms of balancing the building alongside the like some amount of research that is inherently going to have to go into it?
Well, I'm actually very grateful that all the technology we're using has been understood for about 100 years. So it's I would have nightmares to be in Commonwealth's position, frankly, because like you're in the process of attempting to commercialize a thing where there are still like reasonably large error bars on some of the things. For us, the error bars exist, but they're mostly around like just how cheap can we mass produce this thing, and I guess that's where we'll succeed or not, maybe not. We'll find out.
Sure. Lauren, you mentioned runway. So how do you see appropriately managing capital for these inherently expensive, long lead endeavors that each of us are taking?
Build things fast, real things. There's a lot of talk, I like to refer to it as a lot of LARPing out there, of people like, I'm a space company, I have a great logo, I have an awesome building, and I'm like, but where's the hardware? When have you gone to space? And so this idea of like, one, demonstrating, showing rather than telling. It's a lot easier for you to show up at an investor's, on an investor call with flight data and sweet selfies like taken from space. Way more important than look at our design history file. We got to CDR, isn't that cool? Great, but what are you doing? What are you building? And that fits so well into this whole thing, which I love, this sort of paradigm around simplicity and simplest soonest, and de-risking things as fast as you can through validation. I'm a big believer. I used to work in mission assurance and certification, and my job was to convince NASA that the stuff we did at SpaceX like met their requirements. And oftentimes it didn't. And it wasn't because we were like bad at doing things, it was because, you know what, actually, like maybe from a first principles perspective, the requirement doesn't make sense. And so often they don't. And so if you can build the thing so much, like I can't tell you how many things I was able to get out of by saying, you know what, you look at it on paper, definitely not what you asked for. But why don't you crawl inside? Go take a look. Actually put the astronauts in there. See how they feel about it. How are they engaging with it? Wow, not only does this meet the intent of the requirement, this is a way better implementation than the letter of the law said to do. So for me, it's like, how do you remove the conversations, the chatter, the noise, and just get to the hardware?
Yeah, it's really hard to argue when you can point to the thing and say, it's doing it. There it is, right?
Exactly.
You certainly have to like spend the time on the safety aspect. You certainly have to like make sure you thoroughly understand the failure modes. But like, but to your point, you know, requirements have an assumption baked in of how they got there. So something that we face is on the hypersonic side is a lot of the time the requirements assume a subsonic airplane, and you know, even when we talk about like life of aircraft, it's time under wing. Well, time is a terrible metric for talking about life of a hypersonic vehicle. It's really about cycles. How many times have you gone from a relatively cold airplane sitting on the runway to up to speed and then back down? And that drives the life of these systems in a way more direct way than like how long the engine's been running. Because once you're at steady state, then you're not really degrading the hardware in any way. So we have to like, there's a huge amount of education, not only with the regulators, but within the industry and the customer set, both on the government side as well as the commercial sector, on how to be thinking about these problems when you are fundamentally breaking a lot of the assumptions that have gone into all of this, you know, bureaucracy and regulations along the way. Interested to hear how the same sort of thing I would expect to be on the educational front with the stakeholders who obviously want what you're building. Like the market is there, so it's how do you educate people around the approach being different.
Yeah, I think for CFS, we have spent a lot of time explaining how fusion is different from fission. And I've been working quite a lot with both local and state and federal and even international regulators on how do you regulate fusion. There is a little bit of precedent, for those 150 tokamaks around the world that I mentioned, but it's never been done before at this scale. So when we decided to build Spark, which is that device I mentioned we're building right now in Massachusetts, we actually went to the Nuclear Regulatory Commission and said, hey, are you guys going to regulate us on this, or who is the regulatory body? And they said, nope, we actually don't need to regulate this. Talk to the state. So we talked to Massachusetts and spent a lot of time on education of what are the differences, that we do not have any long-term nuclear waste, that there is no risk of proliferation, there is no risk of thermal runaway, going through all of these differences of why we are not fission. I'm very pro-nuclear all around, though, just to be clear. So what we're regulating on for Spark is that we're actually regulated the same as a particle accelerator. So we're actually closer to more of a scientific device as opposed to a nuclear reactor. So that has been really helpful. And we're also part of a fusion industry association. So it's a whole bunch of private companies, labs, et cetera, that are working on regulations at both the national and the international level, and getting those regulations put in place. So by the time we start producing power plants and deploying those around the world, that those regulations will be in place and ideally favorable for fusion.
Right. Yeah, I think that is something that, it's when you're building a business that is, hard tech and in these highly regulated but long lead, hardware-focused, expensive industries, you're aligning multiple things at the same time. You're not only aligning the hardware development, which is hard by itself, you're also aligning the capital and the business plan alongside, and then also the regulations, right? And so it's like threading the needle of all of these convergences that have to happen at just the right time. And that's what, at least for us, is like ends up being some of the most difficult challenges we have to solve, because they are, they're not just complicated. Like the machines that we're building are complicated. There's a lot of moving parts, but they're pretty well quantified, and each part fits together in a pretty straightforward way. But it's inherently complex because these are all human systems, right? You have to convince humans to spend their time and effort on working through these regulations, maybe even putting their own careers at risk because they're taking bets on some of these things. And so I think that's what ends up being the most interesting challenge, is like just aligning with all that uncertainty, all that like, mathematical chaos associated with the human systems around what we're doing.
Yeah, and you need to get those systems put in place like well ahead of, or in parallel with the technology development. When I started at the company, I was the third hire for CFS, and I had somebody start the same day as me who was actually at the very beginning of our movement building team. And so the analogy that we use for the movement building team, their job is to, while most of us are focusing on building the plane, they're focusing on building the runway, so that by the time we're done, we actually have a place to take off. And so I think that's been really helpful of doing that a lot in parallel with the technology, is creating this entire movement around fusion. I think both from a public affairs perspective, but then also from that regulatory perspective, and really laying the groundwork for fusion as a whole industry.
So I kind of want to take a little bit of a different direction now. There was a lot of conversations around approach, which I really love, but I also really love hardware failures. I think that really makes us who we are, when you're building real things, you're inherently gonna be breaking stuff. So I wanna go around, we'll just run down, we'll start with you, Lauren. What is your favorite hardware failure story, given your career?
So I spent a good chunk of my career investigating hardware failures, and so like mostly deep sadness around them. But I'll tell is I was like week 3 at Firefly. I didn't work on that rocket. It was our first launch ever. I did literally nothing. I show up and I'm in the control room, and I'm watching this launch. The thing actually clears the pad, and from my past experience, I'd worked at 2 other rocket companies before. I'm just like, first launch, just don't blow up the pad. Just get off the ground. But then it was like ascending, and it like kept going, and I'm just like, well, is this thing working? This is amazing. Wasn't entirely working. It was sort of not working, and so the range, the people who work at the launch base, they sent a destruct signal to blow the rocket up. It was off course. Totally normal thing that happens when a rocket's off course. But what ended up happening was the debris from that launch vehicle, we were able to collect it, and in order to investigate the failure, we were able to actually walk out and find in a field the engines, the actual piece that failed in the flight. We were able to take those.
That's very rare.
It's super rare. It didn't land usually things land in the ocean, and good luck. This one didn't land on the ocean, and it was in almost perfect condition. And there was some damage, but not from space, because it hit the ground. And so we were able to find the exact place where the failure occurred, take it off of that piece of hardware, bring it back into the lab, run, X-ray it, run all sorts of tests on it, materials tests, and get to the root cause of the failure. And so for me, it's like, yeah, that was a super tragic thing, but another great thing about that, aside from being able to actually diagnose the hardware physically, and I was running that investigation, another great thing was we had a lot of rocket pieces, and so we were able to give the employees a piece of that vehicle, which you usually can't. And so the symbol that I wanted to give to the team was, congrats, guys. Seriously, we launched a rocket. That's amazing. We got some of it back. That's pretty cool. But don't ever do this again.
Yeah. Well, you kind of have to walk the fine line of balancing the celebration of the failure as a learning opportunity. Because if you make it too fearful for folks to do it, then it's like you're not pushing the boundaries. You're not trying, hard enough on these high risk, high reward things. But obviously, you don't want to be negligent, and you want to do something dumb.
Right. It's like, congrats. I mean, literally, how many people on the planet have done this? Very, very few.
Yeah.
And on our first attempt, again, to not blow everything up and to actually get off the pad, that's huge. But yeah, and so to give that team that sense of accomplishment, because you're right, you don't want people to think it's bad to fail, it's bad to make a mistake, but you go, what did we learn from this? All right, we got down to the root cause, let's not make that mistake again.
Yeah, I think to add to that, maybe this is my favorite failure, but something that Lauren, you said reminded me of, for the Dragon CRS-4 failure, the rocket blew up mid-flight. The spacecraft Dragon, which was the vehicle that I spent a lot of blood, sweat, and tears working on, took a big belly flop into the ocean, and we're actually able to recover a lot of the solar panels. And we actually made little tokens, put it in epoxy, and gave it out to every employee, and that sat on my desk for years as a very sobering reminder of how important it is to make sure you're doing things right. So I think that token that you gave to all the Firefly employees, it drives you, like, you learn from that failure, and you learn, okay, let's never do that again. Let's fail fast, but maybe fail hopefully not on a flight vehicle. I think having that memento, like, I still have it at my desk at home, and it's a really somber reminder of paying attention and doing your analysis.
Just echoing what we've already heard. The only truly catastrophic failure is one that you're not allowed to learn anything from. And actually, I've got a funny story to tell here, which is Terraform Industries, we're a relatively young company. We started in April last year in our current facility, and we hired this brilliant intern for the summer called Arun Johnson out of Berkeley, who'd already built an electrostatic fuser in high school. So kind of pretty legit. And it was his job to build and qualify a kind of test scale Sabatier reactor in about 6 weeks, which he did. Just to kind of put this in perspective, this is something that it's a reaction that was discovered in the late 1890s, so quite a while ago. But he built this thing, and it takes in CO2 and hydrogen and makes natural gas with a bit of hydrogen and water vapor and stuff left over. So we're like, that's super cool. Let's burn it, right? Because it's flammable. And so we set it up in a Bunsen burner in the fume hood and lit the flame, and it's this big, smoky, fat yellow flame, and we're like, that's soot. Hydrogen flames are almost invisible, particularly during the day. But this was a methane flame. We'd made it essentially on the first try. We felt pretty smug and proud of ourselves. Anyway, we were kind of tweaking with some of the reactor parameters. And the consequence of that was that the mixture ratio between the hydrogen and the methane became more and more hydrogen rich. The flame was still quite smoky and yellow. But one of the things that we had not fully processed is that what's called the kind of the adiabatic, free flame velocity of hydrogen is about 10 times higher than natural gas. And so what happened was that the flame inside the Bunsen burner actually kind of receded into the tube. And this is kind of like a Home Depot quality Bunsen burner with the side made of aluminium. And so at some point we're just kind of having a look at it, and then it just kind of melts. And we're like, oh, this is not meant to happen. We should think about this, because we're in the process here of making many kilograms of actually, when you measure hydrogen in kilograms, it doesn't sound very impressive. Many thousands of cubic feet of hydrogen every day. If we're not wise about this, we're going to Hindenburg ourselves and feel really dumb. So we kind of had a good conversation about that. We don't flare the stuff off very often anymore. But it was kind of Arun succeeded with his reactor, and we all got to see it working. That was a huge win. And then at the same time, we also got the wake-up call we needed that, now it was for real.
Yeah, one that comes to mind, it also involves hydrogen. Turns out, hydrogen burns pretty hot. We had so this was after we had raised seed funding. We were building a subscale engine demonstrator, basically taking a small kind of crappy off-the-shelf jet engine and pushing it up with our pre-cooler up to high temperature conditions that simulate high Mach conditions. And that's part of our kind of secret sauce, is pushing a jet engine up and then transitioning to a ramjet, which is more efficient at high speeds. So we were doing a subscale demonstration of this, and we had just gotten this metallic 3D printed part, our augmenter, the place where the fuel gets injected and where the flame holders sit for the afterburner. So it's a shared afterburner ramjet combustor. So we had just gotten this piece of hardware in, and at the time it was like a $20,000 piece of hardware. And for us, that was like, oh my God, we're betting the company on this. It's so beautiful. It's gonna be great. So we put in our igniter, and for speed, that we had used a hydrogen torch igniter, so that we didn't spend any time on the development of the ignition system, just because hydrogen always burns. So we put the hydrogen torch igniter into the system, and we're like, all right, let's test it out. And we're like, okay, we'll walk our way up steadily on testing all these systems. And so we turn it on, and in retrospect, obviously very dumb, but a giant, like almost foot-long hydrogen torch inside this piece of hardware that's only maybe 9 inches in diameter. We blew a hole inside the combustion liner immediately, and we look at it and we're like, oh, what are we gonna do? Like, we can't buy another one of these things. What are we gonna do? And Glenn Case, one of my co-founders, he was like, it's okay. So we got some of it was an Inconel part, so we got some like Inconel sheet and like ran some quick runs on it. An interesting thing is if you shoot that hydrogen flame at a flat piece of Inconel, it does not burn through it, but because it was slightly curved, it like focused all the heat in, and we would burn through it, and it looked exactly like it. So it was like, that was an interesting piece of learning there. But drilled some holes in it, and he tack welded it inside, and we ran our entire engine test campaign with just a tack welded piece of Inconel sheet in there that we just had gotten on McMaster and just made it work. And so all of the technical learnings came about from this like scrappy solution to a hardware failure that is like part of the culture that we always want to embed, is like the scrappy approach to things, and like figure it out, and like you're always going to hit these issues. But that one will live on in my mind.
Yeah, I think what you're saying, Glenn was saying, this is okay. Right? I think that's something that's like super important to realize and to learn and to accept in doing hardware type work, is that it is okay to fail. It is okay to try and something doesn't work. And that is better, you will learn something more through that approach than being too scared to try. In one of the early days at CFS, we were working on this new prototype for equipment, and two of my engineers were working on this, and they seemed really nervous to take this next step. And they're like, well, I think I want to try this, but I don't know if it's going to work, and this is super expensive, and we're going to scrap all this material if it doesn't work. And it's like, do you think it's going to work? And you're like, what's your probability on there? Like, yeah, I feel pretty good about this. And I was like, great, then try it. And
send it.
And just like the look in their face was, wow, I can do that. And like, it is okay for me to put hundreds of thousands of dollars worth of hardware at risk. And I was like, yeah, because you're going to learn something from it. And you know what, it worked. And yeah.
Yeah, you definitely have to make sure, your CFO or your finance people have that in mind.
Very true.
You have to create the systems that enable that to be possible. But that's
like, because they tried this out, we ended up finding a new method for manufacturing that was twice as fast as the old way that we were doing it.
So yeah, the financial savings, even if you had wrecked that hardware, end up paying themselves back. That's really cool. Cool.
I broke down our burn rate by like per person per day and so on, so that people can have an intuitive understanding. Put this up on a big whiteboard right by the front door. Every morning they come in, they know that like, if I just sit at my desk doing nothing all day long, like my per head cost is $1,500 or something. And so whenever they're trying to decide like, oh, should I expedite this part or whatever, like if they're on the critical path of the whole company, that's obviously like, that's a very big number. But even for themselves, it's just like a waste of their time to sit around not doing anything because they're waiting for a part to come in for 3 weeks. So it's really important to teach people the time value of money.
Yeah, that is a number that our CFO, we worked out and share very readily with the entire company. Of if you are on critical path and you save X number of days, this saves the company this amount of money. Therefore, the trade is worth it.
So to kind of wrap up, the title of this panel is Atoms versus Bits, but I want to take it down the direction of like places where you see software really enabling this technology. I think a lot of our focus has been maybe even back to like, the early 1900s where it's like, try things, break things, figure it out, move on. But where does the modern world have to play in terms of like really accelerating things and really helping bridge, or like helping to be complementary to the more, early 20th century approach? Lauren, do you want to start?
Yeah. Less food delivery apps, more things that matter. Just gonna say it.
Amen to that.
I think people look at the stuff that, if you're gonna build a rocket, it's not just I need a structures engineer and someone who understands propellant and engines. There are supply chain folks, there are software engineers, there are material scientists, it just goes on. And that's why it's so expensive and it's so hard, is because there's so many disciplines and so many people who need to come to the table in order to build these things. And in the past rockets, we were just like, well, if I have a structure and I got some high energy fluids, I put them together and like get energy, it goes up. But like, when you start to add the software piece to it, and when software engineering in terms of like being smart about how we control these things. Like when you see these rockets landing, 2 of them at the same time on a pad, that's not just like a bunch of structural engineers being like, yeah, we got this. Like, no, that's like a ton of precision. That's like, man, those things could crash into a building and like destroy a place, but that's not what's happening because they're some of the most kick-ass, amazing software engineers I've ever seen are working on this. And in the past, if you look at the space shuttle, the astronauts used to actually pilot that thing to like drive it into dock. They would still like steer it and stuff. And like now, you put the astronauts in Dragon, and they're like, "Where's the joystick?" Like, there ain't no joystick, dude. Just sit there and enjoy the ride. And so. And it's just going to get more and more autonomous. When they landed on the moon, same thing. Like they're doing literal hazard avoidance. And like, I worked on the bid, when I was at Blue Origin, our bid to land astronauts on the moon, and being in these conversations with NASA, and they're like, yeah, so like how do the astronauts, do the joystick thing? And you're like, well, why would they need to do that? Yeah.
Safe with the
exactly.
AI.
Just sit back, chill, and yeah, there'll be an override because, first of all, the machine's going to respond way faster than any human ever could imagine responding. However, they're unknown unknowns, and if I'm on the moon, I want to have some control over my fate if the machine gets it wrong. But that's not the baseline. And so I am so excited to see the aerospace industry embracing autonomy, embracing cybersecurity, and that's going to be a huge thing in the future. And so my call to action to anyone here who is a software engineer, developer, or knows people who are, it's like, stop building stupid stuff and come and build things to change the world. We need you.
Yeah, I think one of the reasons that we've seen such explosive gains in software productivity is that we've built this like really impressive tooling stack from like assembly all the way up to like generic, high-level languages that enable dumbasses like me to write code that does extremely powerful things in essentially my spare time. And we don't have that for manufacturing, right? So like prior to about 1900, we only had like hand-making stuff. And then since then we got, standardization of parts and mass production, developed mostly by Ford initially in the automotive sector, but that's since grown into other areas. And that certainly delivered great cost savings, but we're still at the point now where if you want to have a physical device that's a consumer item that is cheap enough, you need to go out and build a gigafactory somewhere. You need to spend $1 billion, build a factory, get the tooling together. That's not the case with software, right? If I want to tomorrow, I can go and pull a bunch of Python packages out and put them together and make something completely new that'll probably work on the third try. And the cost of failure is almost zero. And so the cost of experimentation is almost zero. The productivity and creativity enabled are enormous. We don't have that for hardware. We do need it though. I just want to be clear, like if we want to have a really cool future, energy, like solving energy scarcity is a big part of it. But I mean, I've been known to write blogs about living on Mars. We won't be able to do it if we don't have the ability to abstract human labor away from like physical manufacturing of actual atoms and stuff. So people need to work on this. It's a really hard problem. I don't think it's even fully conceptualized.
Yeah, I agree. I think we need both. We need software, we need hardware. And similar to what Lauren was mentioning for rockets, the tokamak is a very large, mostly steel and concrete structure, but it is also a living and breathing machine once you turn it on. And there's a whole bunch of instrumentation and controls on how do you monitor that, how do you find the right conditions. We will be getting more into machine learning with the device as well. So actually having it, learn from itself during these runs and getting more and more efficient reactions out of that that would not be possible if we didn't have those software components. And then, in addition to software for the device, there's also, all the software for running the manufacturing facility as well. So that's everything from, the instructions, work instructions. We need a software package to write that. It controls all of our equipment. So it's like, yeah, we really need that software. And I will very much echo Lauren's plea of, please, if you are a software person in the audience, please spend your brain power for something good and put that towards, something good for the planet and supporting hardware projects.
Yeah, I think it's similar and tangentially related to all those things where we talk a lot about at Hermeus, we're not just building the airplanes, we're building the machine that makes the machine. So a lot of that comes down to enabling people to make high quality decisions because you can't centralize that. And it is easy to like even have like a pull towards that where it's like, people get promoted, they obviously because they're very smart. And so it's like this tendency of like to consolidate decision making. So, but really the way that you combat that is by driving contextualization to the rest of the team. And I think by having the right instrumentation, not only in the machine itself, but in the machine that makes the machine, then you can drive that context to the rest of the team and allow them to make decisions as close to the edge, as close to the hardware as possible. So I think enabling that, and so it's like it's everything from not only machine uptime and all the details there to like your ERP system, like how finance is being run, like where you're at on runway, and like especially with like the types of folks that we're all probably looking to hire, it's like they're more than just that technical skill that you're hiring for. So it's like enable people to really make those decisions. So it's really using the software stack to drive that contextualization. And it's really, really complicated to be able to do that because there are so many moving parts, but it's something you have to like spend intentional investment on to really drive it. So yeah, final thoughts here. We're on the 2050 track. Let's talk vision for 2050. Where our companies are at, where they're going, and like what does the world look like in 2050? Something that we like to talk about at Hermeus is that we went back and looked at when we increase speed of transportation between major city pairs, what does that do for the economy? So for us, we looked at, Roman roads, we looked at high-speed rail in China, and extrapolated, and there's a lot of assumptions that go into this extrapolation, but when you can connect major city pairs at roughly 5 times faster of air travel, what does that do for the world? And so from our analysis, it's something like $4 trillion per year of GDP growth. And that's 2% of the global GDP. So this is something that's significantly high impact to the world, is just by reducing the friction of ideas, of goods, of connectivity between these cities that I think is really, really exciting. And then you can use those resources to fund other investments and it just compounds further. And none of that could happen though, except for like with the work that y'all are doing. So I'll turn it over to Darby.
So for Commonwealth, our goal is that by 2050, we'll have 10,000 fusion power plants running around the world. That is in every country in the world, focusing on a really equitable distribution of energy. With that as well, the world's energy demand is actually going to double in the next 30 years. So when we talk globally about getting to net zero by 2050, it's not just meeting the demand of reducing carbon emissions in today's world. It's also thinking about how that will double in the next 30 years. So the goal with 10,000 power plants, that's roughly 20% of the entire world's energy supply. So that is a very ambitious goal for us to get to in the next 30 years. And it's actually something I'm super excited about from the manufacturing perspective is how do you build the factories to build those power plants and deploy those around the world? That's the goal.
Yeah, 2050 is 27 years away. By then, we will have capped every last oil and gas well, closed every coal mine, and people will be enjoying gasoline for $1 a gallon, not including inflation, obviously. So I just want to be clear here, like this is not something where you have to, you can if you want, you don't have to become vegan or something in order to buy this future. Like this is a future where we have unconditional energy abundance for everyone, not just Westerners, and the gas is cheaper and it's higher quality and it's also carbon neutral. It just solves that problem. And we'll end up spending most of it because electrification of transport, I'll end up spending most of it on high-speed planes, I think, and plastics.
All of these things will be true.
Definitely.
Plus, in my version of 2050, you've got a human presence. I could see a space station, a commercially owned and operated space station around the moon, around Earth, around Mars. But none of that makes sense if we have war and famine and a terrible planet here. Because you will not get the funding, you will not get the public support if we're leaving people behind. And if we're gonna make a future like that, where we are a multi-planetary species, we can't screw it up. And so I think what that means for back here on Earth is there's abundant energy, there's water, there's clean air, and the poor and marginalized people on the planet aren't being left behind and told to just deal with it. Because when that happens, you have war. And so we're not going to be circling around Mars if everyone is spending all their money and energy nuking each other.
Thank you very much.